Welcome also from my side. My name is Joschua, and today I'll present our paper, which is joint work together with my colleagues from CISPA as well as FAU. I'll start with the second part of the title, so why sanitizing on the binary level is hard. And after that, I'll also talk about our binary level thread sanitizer. For those that are not too familiar with sanitizers, here's what you have to know about them in a nutshell. Basically, sanitizers are runtime checks which are added to a program in order to detect errors or even vulnerabilities during the execution of the program. In addition to that, they can also help with debugging as they provide additional information about found errors like stack traces, for example. So how does it work? How do you use the sanitizer? If you have source code for your program, you can just compile it and add a specific compiler flag, which is usually called fsanitize, and then you have to specify what kind of sanitizer you want, because there are different kinds of sanitizers for different kind of bug classes. If you use this flag, the compiler will link your code with a sanitizer library and will also add instrumentation into your program. So this instrumentation are basically calls into the sanitizer library, which implement these additional sanity checks. This will then result in a sanitized binary, and these sanitized binaries you can use in the same way in which you would use a regularly compiled binary. However, a typical use case for sanitizers during the last years have been fuzzing. So if you execute your sanitized binary and you actually find an error and that error is executed, you will get a warning which might look like this and usually contains additional information and a stack trace. So in general, this is a very well-established process which has been working for a long time. However, there's one big problem, and that problem is that it doesn't work if you don't have the source code, because most sanitizers are not available for binaries. They only work with the source code. This is what we call the binary sanitizer gap, because on the one hand, you have these great tools for source code applications. However, in the real world, you very often don't have the source code because you have closed source applications. When we first found out about this, we were interested in what caused this gap. So we looked into challenges which could potentially impede the development of binary sanitizers, and we found two large categories, two large groups. The first one is information loss, which refers to basically all the information that is just lost during the compilation, so that the binary sanitizer, contrary to its source-based counterpart, has just less information to implement these sanity checks. The other big category is conceptual differences, and for this you just have to know that these original source-based sanitizers were usually thought with high-level language concepts from languages like C or C++ in mind, and then they were implemented usually in compiler intermediate representations. And on the other hand, we now have binaries, so we have assembly, in our case x86 assembly, where just completely different concepts are applied, which makes it pretty difficult to port sanitizer to the binary level. We listed a couple of examples here if you're interested in that. More is in the paper. I do not want to go into too much detail here because it really depends on what sanitizer you look at. So let's have a short overview of the current landscape of sanitizers. Here you can see the four most popular ones, and we will also look at whether a binary port exists for both. Probably the most popular sanitizer is address sanitizer, or ASAN, which detects memory corruption. And it's actually the only one for which a binary port exists, which is called ASAN Retrowrite, which was published a couple of years ago. And ASAN Retrowrite basically reuses the runtime library of the source-based sanitizer and then just adds instrumentation to the binary, which produces sanitized binaries which work in many ways the same that source-based ASAN would work. So now let's have a look at the other sanitizers and why there have been no development for them. The first one we want to look at is memory sanitizer, or in short BINTSAN, which detects uninitialized memory. And at first look, it looked really similar to ASAN. However, the problem is that the instrumentation here is much more complex. And one of the reasons for this is that in order to detect errors related to uninitialized memory, you have to track this uninitialized memory through the program. And if you want to do that, you basically need to consider every single instruction which might interfere with this memory or might touch it. And if you work within a compiler, so you have compiler intermediate languages which have a reduced instruction set, this is doable. However, if you have x86 assembly with a very, very large instruction set, it's basically infeasible to handle every single instruction in x86. So we regard binary BINTSAN infeasible. Next, have a look at undefined behavior sanitizer, which, as the name suggests, detects undefined behavior, which is already a high-level language concept because it basically refers to that the compiler isn't really sure what the programmer wants and doesn't therefore know what to do. However, if you have binaries, if you have a binary file, obviously the compiler has decided to do something, and from that something, so from the binary, it is really hard, or in most cases actually impossible, to really know what the original source code might have looked like and whether it contained undefined behavior or not. We looked at the 28 checks in USENIX and found only 11 that were at least partly possible to implement on a binary level. Finally, this leaves us with thread sanitizer, which detects data races. And that one is actually really close to ASAN, or very similar, as it also has a runtime library which does the actual error detection, and the instrumentation isn't too complex. However, there's a problem with lost information, again, due to different concepts between a binary and higher level languages, which regards information like atomicity and memory order. However, this information is in many cases not critical for a working data race detector. Therefore, we consider TSAN actually feasible to port to the binary level, which is what we did. But before we look into TSAN in more detail, or binary TSAN, let's have a short look at binary sanitizer architecture in general. So this is source-based architecture for source-based sanitizers. However, if you do not have the source code, obviously you can use the compiler. So you're just left with a binary that is not sanitized yet and the sanitizer library. If you want to change the binary, you can use something like a binary rewriting framework, which allows you to add additional code or additional instrumentation to the binary. And for this binary rewriting framework, then you can implement a sanitizer plugin, which on the one hand adds the sanitizer library to your already compiled binary, and on the other hand adds these instrumentation checks into the already compiled binary. So together, the sanitizer plugin and the binary rewriting framework are the binary sanitizer, which produces sanitized binaries that behave in the same way that regularly sanitized binaries behave. So you can also use them for fuzzing, for example. Now let's have a short look at what we did at our implementation of BINTSAN. So as I've mentioned, we have the thread sanitizer library, which does all the heavy lifting. So it does the actual detection of the data races. Then we instrument basically all memory accesses. And in addition to that, we also implemented call stack recording so that we can give additional feedback and give stack traces about the errors that we detected. If you interfere with binary, you also have to consider the state of the binary. So if you add instrumentation, you have to save the state, in our case, the registers, before that interference, and have to restore the same state after your instrumentation. In addition to that, we also have optimizations that we implemented. Some of them are specific to our problem of data races. Others are more general and can be used in binary sanitizers as well. So finally, this leaves us with the problem of information loss, which I mentioned earlier. And to overcome this, at least to some degree, we implemented heuristics to detect atomic operations in BINTSAN. So let's have a short look at how well BINTSAN works. So we evaluated our tool with over 40 applications and compared it to the source-based thread sanitizer and the current state-of-the-art tool in binary data race detection, which is called Helgrind. As the source-based sanitizer is our gold standard here, we see it as our ground truth in this experiment. So every data race that is found by the other tools that matches a data race found by source-based TSAN, we consider a true positive, and anything else that is found, we consider a false positive. In general, for most or for the vast majority of applications in our dataset, BINTSAN performed really well, as it produced absolutely the exact same output as thread sanitizer would. However, there are some exceptions. The most notable one is FFmpeg, where we have a lot of false positives and a lot of false negatives. And there are a couple of reasons for this. One of the main reasons is that FFmpeg uses a lot of these atomics. And if we cannot detect these atomics by our heuristics and the heuristics fail, obviously, we will get false positives and false negatives. Still, we are much better than Helgrind in every regard, which doesn't have these heuristics. Finally, let's have a short look at the performance of our tool. As you would expect, source-based thread sanitizer is the fastest. Our tool BINTSAN is a little bit faster, a little bit slower, sorry. It has an overhead of about 15% on average, and which is still way faster compared to something like Helgrind, which uses dynamic instrumentation and is 5 times slower than our tool. So if you're interested in the project, please check it out. The paper is published now. The code is also available. Thank you for listening. Now I'm ready for your questions. Thank you.